All right, so welcome future Physics 30S students to my voice. Yeah. As I was telling these guys, part of the Pan-Canadian is to be scientific literate, and part of that is reading and using a graph. So we're going to spend a few days just sort of reviewing our skills about graphs. So follow along with me here, please. A well-designed graph is more than a picture with 1,000 words. It can give you more information than either words, columns of numbers, or equations. To be useful, however, a graph must be drawn properly, and in this section we'll develop the use of graphs to display data. So again, it's a graphing review. One of the most important skills to learn driving a car is how to stop it safely. Who's taken or is in driver's ed right now? Excellent. Okay, so you all are sort of somewhat familiar with the stopping distance, and in one of the concepts in grade 10 science is to talk about stopping distance. So we're going to sort of use that as our vehicle, if you'll pardon the expression, to learn about graphing. No car can stop on a dime. The faster the car is going, the farther it travels before it stops. If you studied for a driver's license, you probably found a table in the manual showing how far a car moves beyond the point at which the driver makes a decision to stop. And from what I understand, that isn't really taught as scientifically as it once was in the driver's ed program. One manual shows that a car travels a certain distance between the time the driver decides to stop the car and the time the brakes are applied. This is called the reaction distance, and here's where a highlighter would be a wonderful thing to have. If you don't have a highlighter, you could just use a pencil or something. I'm just going to try to find my highlighter. It's been a while since I've done this. Yeah. Is yours a little different?
Yeah.
Oh, okay. You know what? I keep saying, yeah, okay. Thanks, Riley. All right, so Riley has pointed out that I was using the wrong... Yeah. Well, yeah, actually, I've simplified this quite a bit, haven't I? Good for me. Okay. So when driving, there are two parts to the total braking distance: reaction distance and braking distance. So what is the reaction distance? Do you remember that from grade 10? It's a distance column. It's reaction distance. So it is, to write this in a proper sentence, it would be the distance, right? We could just, because it's kind of point form, we could just say distance traveled in what time? During the reaction time. And I'll try to write neat for future students so that they can read it. Distance traveled during the reaction time. It's the distance you travel in the time it takes for your brain to say, oh, move from the road, foot hits the brake, right? So it's like that half a second or so that it takes to get your foot actually on the brake. What is the braking distance? How long? Distance. You know, that's an interesting thing, Colin. I'm glad you brought that up. Canadians tend to measure distance with a time. How far is it to Brandon? About 2 hours. Oh, a boot, 2 hours. Right. A. How far to Calgary? A boot, 12 hours. A. It's not 12 hours, it's 1,200 kilometers. It's the distance. I do it all the time. How much farther? 2 hours. It's the distance traveled. Oh, I switched color. Distance traveled while braking. Please notice that braking, referring to your car brakes, is B-R-A-K, not B-R-E-A-K. That's like when your car falls apart. That's the braking. Okay, so it's the distance traveled while braking. Okay, this table shows both based on various speeds. Now, all of this is dependent upon how good your brakes are. If you're driving my mother-in-law's car, your braking distance is going to be considerably more because that car desperately needs a brake job. I hope she's not listening to this video. She says it's safe. She's wrong. I don't think she's going to hear this. Okay, so this table shows both based on various speeds. Now, original speed in meters per second. In physics, we tend to deal with meters per second, and we dealt with those of you that saw me for grade 10 science, and I'm sure other teachers do the same. We tend to deal with speeds in meters per second, right? Generally, people are more aware about kilometers per hour, so this is an excellent opportunity for me to remind you of the magic number, which is 3.6. Do you remember the magic number 3.6?
No.
Future Physics 30S students, half of you should be putting your hand up right now because you remember the magic number of 3.6. Okay, so what I want you to do is take your scientific calculator that you brought to class, and I want you to take the meters per second, and I want you to convert to kilometers per hour. And how do you do that? By multiplying by 3.6. And those of you watching the video right now, Mrs. Malcolm, you should press pause. And I'm going to give these guys about 90 seconds to do that. Yeah, you were supposed to have done them all. You should, maybe let's just make a note here on the margin. If you're going from, and there's a little bit of room over here, so that's good. If you're going from meters per second to kilometers per hour, you're going to multiply by 3.6. You have to make it a bigger number. And if you're going from kilometers per hour to meters per second, you're going to divide by 3.6. Now, if you're one of those people that wants to create their cheat sheet as they go along of all those important concepts, or at least make a note of it, make it on your cheat sheet, that's certainly one of them. How many people over the years do you think have screwed up whether it's multiply or divide? About 20%. And so they end up with a car going 4,000 kilometers an hour. Think about it, you guys. Okay, they get it going the wrong way. Yeah, so just think. You would think they would, Riley, but some people just blindly write down whatever number's in the calculator, whether it's right or wrong. Or, yeah. Okay, so what's 10 times 3.6? I'm really hoping no one went 3.6 times 10, but I know some of you did, and then felt silly when you did it, didn't you?
Just to make sure.
Just to make sure. 36 kilometers an hour. So if you're going 10 meters per second, that's only 36. 15, help me out here. 54. So like 54 would be like, you know, a little over the limit in town, right? 15 meters per second. That's pretty far. Like how far is 15 meters? For those of you that can't see me because you're in this afternoon's class, I'm pacing around the room like a lunatic. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's only 10 from there to there. Okay? It's a little bit more the other way. So we're talking easily the width of this room plus half of Mrs. Coombs' room next door, and you're only going 54. That's how far, or that's how fast you're going. 15 meters, you're going that far in a second. 20 meters per second, 20 times 3.6, 72. You know, that would be like down by ACC, that kind of speed. 20 meters per second, 25 meters per second, I think it's like, is it 90?
That's what Colin drives on Main Street.
Yeah? Well, maybe something you learned today might encourage you to not do that, Colin. If you're going 30 meters per second, I think it's 102, right? What is it? 108. Oh, I don't even know how fast that is. I've never been going that fast in my life. My car doesn't even go over 100. So yeah, if you're going 108 on the highway, you travel 30 meters in a second. That's about the length of the hallway here, down to the bathrooms, down to the windows. A second. It's just math, man. You know those yellow lines on the road that tell you when it's okay to pass or not, the dotted ones? How long do you think those are? 10 feet. Yep. You know why they look like they're this big? Because you're driving 150. In our example, the speed of the car is the independent variable. I'm using finger air quotes here for those of you that can't see me. Okay, independent variable or the manipulated variable, because it's the one you have control over. Okay, so it's the speed is the independent variable or the manipulated variable. Yes, Thomas. That's like why movies look like they're moving when it's really just a series of pictures. They're moving so fast your eye can't recognize the difference. slow down. The list of kids that I've taught over the years that have died in car accidents is already long enough. It's true. I can write the list on the board if you want. I don't like doing it. By the way, what I didn't do is I didn't give you the reaction. So if you're going 10 meters per second, it takes you 7.4 meters just to get your foot to the brake, and then another 9.1 to actually stop for a total of 16.5. So if you're driving at 108 on the highway, it can take you up to 100 meters to actually stop.
That's on the brakes or the brakes?
Well, there's a lot of factors here, right? But I mean, that's kind of an average. 100 meters, that's a long ways. Okay, back to what I was talking about. In our example, the speed of the car is the independent variable or the manipulated variable. The other two variables, reaction distance and braking distance, change as a result of the change in the speed. These quantities are called dependent variables or responding. Okay, so you need to know the difference between independent, what you have control over, and dependent. You can adjust the speed, and as you adjust the speed, the braking distances change. So the speed is independent, the braking distances are dependent. Now, how do the distances change for a given change in speed? Notice that the reaction distance increases by about the same amount for each increase in speed. We're going up by 5 meters per second here each time, and these differences are kind of about the same. Like 7 to 11 is like 3, 11 to 14 is like 3, 14 to 18 is like 4, and there's some decimals here. 18 to 22 is like 4, so it's somewhere between 3 and 4 each time. They're going up by the same amount, which isn't surprising. But it's kind of hard to see because they're decimal numbers. The braking distance, however, increases much more as the speed increases. So this is here is 9.1, then it goes to 20. That's a difference of like 11. 20 to 36 is 16. 36 to 57 is 21. It's going up more and more and more. It's changing differently. It's a different relationship. The relationship between the distances and the speed can be seen more easily if the data are plotted on a graph. You can't tell me what kind of relationship it is just by looking at numbers, unless you're some sort of genius. To avoid confusion, you should plot two graphs, one of reaction distance and the other radius. And in fact, what I did was 3. Do you have that graph? You should have it, right? You'll notice that the reaction distance is what shape? What shape is that, Riley? The blue one. What's the shape of the line, of the graph? Is it a line? Yeah, it's a straight line, right? It goes up by the same amount each time. It's a straight line. But the red one is what? It's curved. The red one is curved, and in fact, the green one is when you add those two together. So when you see one is a straight line and one is a curved line, that tells us that the relationships are different. Different. Okay, so that's why we do graphs. Okay, so here are the steps for plotting graphs. I realize you know all this, or I'm hoping you do. Yeah, I should have put the page. Again, this is just kind of review. So these steps will help you plot graphs and data tables. Identify the independent and dependent variables. In other words, which goes on the x and which goes on the y. The independent variable is plotted on the horizontal or x-axis, and the dependent variable is plotted on the y-axis. Right? In our example, speed is plotted on the x, and distance is plotted on the y. So you've got speed and no. Little pause here while my computer works. Come on. Yeah. I gotta be careful where I lean. I press buttons. Okay, I thought I was gonna stop the recording. That would have been bad. Okay, so what I was trying to do was I was trying to do this. Speed and distance. Independent is on the x, dependent is on the y. There are times when I'll reverse them, and I'll give you that reason why in a bit. But most of the time we do it that way. Step 2, determine the range of the independent variable to be plotted. What do I mean by the word range? In math, what does range mean? From highest to lowest or lowest to highest, right? So determine the range of the independent variable to be plotted. In the example, data are given for speeds between 10 and 30 meters per second. Now, if we start at 10, could we start at 0, and should we include 0 if we can? Yes, you're right. If you can at all include 0, you should. So a convenient range might be 0 to 30. Decide if the origin is a valid data point. The origin is at 0, 0. If you're traveling 0 meters per second, what is your reaction distance? 0. So is 0, 0 a valid data point term?
Yes.
Are you going by what they're saying, or did you come up with that answer on your own? You didn't convince me. You know why? Because you were distracted by Savannah. Savannah, don't distract her. She needs to listen. Savannah, is 0, 0 a valid data point?
No.
I don't know.
You don't know?
Well, it doesn't seem right because there's 2 zeros.
Well, where is 0, 0? 0, 0 is right here.
Yeah.
Okay. So, if you're going 0 meters per second, what's your reaction distance? 0. You should already stop. So it is a valid data point. You should include it. When the speed is 0, reaction and stopping distances are obviously both 0. In this case, then, your graph should include the origin. Spread out the data as much as possible. If you've got a great big sheet of graph paper, don't put it in 1 square inch in the corner. Make it big. Let each space in the graph paper stand for a convenient union. Choose 2, 5, or 10 spaces to represent 10 meters per second. Number and label the horizontal axis. So put all your numbers. Tell me what it is. Label. Mark coming on the upcoming future lab if you don't label. Hint, hint. Label, speed. Repeat steps 2 to 4 for the dependent variable. Plot your data points in the graph. And then number 7 is important because every student doesn't want to do this. It says, draw the best straight line or smooth curve that passes through as many data points as possible. Do not use a series of straight line segments that connect the dots. I repeat, do not connect the dots. Okay? I know at some point they talk about, why is the word escaping me in math class? They talk about data. Continuous versus discrete. Is that what they said?
Something, yeah.
Does that, yeah, Megan? Did I get that right? Okay. So if it's discrete, that means that they are single points and you should not connect the dots. And if it's continuous, that means that something exists in between, you still shouldn't connect the dots. Now I know that teachers teach this to connect the dots. They're wrong. They're wrong. Okay? Because a graph is to show the overall trend, the overall sort of average relationship. Do not connect the dots. Wrong. Give the graph a title. Okay. I realize that I'm trying to cram in as much as I can because I've got a limited time to it. So please bear with me. We've got about 10 more minutes. I'll probably be going right to the bell, you guys. Linear, quadratic, and inverse relationships. Okay, so there's 3 types of relationships that you should know. If you're following along on that exam review, you will notice that one of them is know the 3 types of relationships. Here they are. Linear, quadratic, inverse. The graph, figure 2 of reaction distance versus speed is a straight line. That is, the dependent variable varies linearly with the independent variable. There is a linear relationship between the 2. There is a linear relationship between the 2. The relationship of the 2 variables shown in this graph can be written as an equation, y equals mx plus b, where m and b are constants called the slope and y-intercept respectively. How many people have ever heard of y equals mx plus b? Excellent. M is the slope, b is the y-intercept. You should know this. The slope m is the rise over the run. You've heard rise over run, I'm sure. You absolutely must be able to calculate slope to continue in grade 11 physics. You have to be able to do slope. Okay, so let's pick 2 points here. I've picked 10 and 7.4. So this point right here is at 10, 7.4. Remember, the x comes first. Grayson, gotta be paying attention, man. Engage with me. 10 is the x, 7.4 is the y. We've got that off our data table. And the other data point I picked was this one right here. And this point is at 25, 18.5. Okay, so rise over run, y2 minus y1 all over x2 minus x1. So I'm going to take my 18.5, subtract 7.4. There it is right there. And I get 11.1. Then I'm going to take my 25 minus 10. There it is right there, 25 minus 10. And I get 15, and when I divide, I get 0.74s. 0.74s. What does the S stand for? Seconds. Notice that the units have been kept, but the variables and the units for the slope are seconds. The slope has a unit. Now that's something that they might not touch on too much in math class. I'll be expanding on that. That's something that I feel is important. Thus, it is a time, the reaction time. The slope is the reaction time. I'll say it again. And just because it's not on the page doesn't mean it's not important, doesn't mean you shouldn't write it down. The slope is the reaction time. The slope refers to the reaction time. I know that because it's in seconds. What do we get out of this? We know that the person driving this car takes how long for their foot to get to the brake? 0.74 seconds. It's their reaction time. It's not bad. Could be worse. It is the time your body takes from the instant the message to stop the car registers in your brain until your foot hits the brake pedal. It's the time for your foot to get to the brakes. Thus, the slope is a property of the system that the graph describes. In other words, the slope has a meaning. It's not just a number to make math teachers happy. In science, the slope has a meaning. One of your jobs will be to figure out what that meaning is in various situations. It's going to take some thinking. Okay, now what about the y-intercept? What is the y-intercept? Do you remember? It's what? It's the point at which the line crosses the y-axis and is the y value when the value of x is 0. It's this point right there. It's the y value when x is 0. In this case, when x is 0, the value of y is 0. How come? Because Savannah told us that the origin is a valid data point, and it said when we were traveling 0 meters per second, my y value is 0. So the y value was a 0. We can also see that right on the graph, because where does it go through? What point does it go through? Right there at 0. This means that when the speed is 0, so is the braking distance. Okay, the value of y does not always increase with increasing x. If y gets smaller as x gets larger, then delta y over delta x is less than 0, and the slope is negative. This is a negative slope, right? You guys know what positive slope, negative slope? You should. See how it's all coming back to you? I'm kind of bringing that review stuff back, getting everybody sort of up to speed. Get it? Up to speed. Thank you. Thank you very much. I'm here all week. Tell all your friends. Oh yeah, I'm leaving at 1:30 right there. Okay, another kind of relationship. Quadratic relationship. I had a quadratic relationship in high school. I was good at square. Okay. Yeah. The graph of braking distance versus speed is not a straight line, but rather looks like a parabola. Have you heard the word parabola before?
Yes.
This indicates that the braking distance varies as the square of the original speed. In other words, if you double your speed, the braking distance increases 4 times. I don't know if they teach you that in driver's ed. Double speed, braking distance increases 4 times. The graph's slope changes, so it cannot be calculated. Can you find the slope of a curved line? You cannot. You can, however, calculate the slope of the curve at an instant by drawing a tangent line. That's something we're going to get into in the future. Tangent lines. That's supposed to be straight. Question. If it takes a person 40 meters to stop after driving at 50 kilometers an hour, how far will it take them to stop driving at 100? Remembering that it's not a linear relationship. If it takes you 40 and it's not going to be able to read off the graph column. Good thought, but if it takes you 40, this is my little test to see if you've been paying attention. If it takes a person 40 to stop after driving 50, how far will it take to stop if driving at 100? 160, 4 times. If you double your speed, the braking distance increases 4 times. 4 times. 4 times 40, 160. Good job. Okay. Inverse relationship. Some relationships are such that as one quantity increases, the other one decreases. This is called an inverse relationship, and its graph will look like figure 5. Again, you may only determine the instantaneous slope by applying the tangent line method. This is just made up numbers. Inverse relationships have this curve to them. You cannot find the slope of a curved line again. So you've seen linear relationships, straight line. You've seen quadratic relationships where it's curvy, parabola. In math class, parabolas generally look like this. They do both sides, right? But in the real world, can you have negative time? No, so you only get the right-hand side. This is an inverse one right here. Okay. I've actually got everything done that I need to. The afternoon class is gonna get time to work. You guys aren't. Okay? I'm gonna ask if you could for tomorrow, this morning class, or for Monday, could you guys try questions 1, 2, 3, and 4? You will have some trouble. I usually do one and then give people a little more time. I usually do that kind of thing. I'm not obviously able to do that. It's 10 o'clock. But give questions 1 to 4 a try over the weekend, and then we'll try to get you guys caught up to the afternoon class on Monday. Okay? And we're going to spend some time, that was sort of the introductory, we're going to spend time practicing graphing as well, and we're going to do a lab as well next week. So that is all. Thank you for your attention.